We are going to discuss about derivation of continuity equation in a 3D, a three-dimensional flow. Continuity equation, three-dimensional flow. Continuity equation, three-dimensional flow. So before going to solve the continuity equation for three-dimensional flow, we should follow, these are the steps in the derivation. The first point is principle of conservation of mass. What is the definition of principle of conservation of mass? And consider a small fluid element, that is the second step. And third one, mass of fluid entering the phase AB, that is the inflow, and mass of fluid leaving the phase EFGH, that is the diagram I will show later, that is the outflow. And also what is the gain of mass in x direction, what is the gain of mass in y direction, gain of mass in z direction, and the net gain of mass, that is the x direction, y direction, and z direction, what is the net gain of mass. Then what is the mass of fluid, what is the rate of increase of mass of fluid. Finally we are going to get that gain of mass of fluid must be equal to the rate of increase of fluid in the fluid element. These are the steps involved in the derivation of continuity equation, three-dimensional flow, continuity equation. Now we are going to discuss about one by one. Three-dimensional flow. Here, what is the principle of conservation of mass? Principle of conservation of mass means the rate of flow at one section must be equal to the rate of flow at the another section. That means, same way, this is one pipeline, this is the section 1-1, this is section 2-2, the rate of flow at section 1-1 must be equal to rate of flow at section 2-2. That means Q1 is equal to Q2, or Q1 is nothing but area into velocity, that is equal to area into velocity. This is nothing but principle of conservation of mass, right? This is about principle of conservation of mass. Then we are going to take one small fluid element here. In this fluid element, this is the x direction, the fluid element length is dx, this is y direction, the fluid element length is dy, this is z direction, the fluid element length is dz, and the velocities components in the x direction is small u, in the y direction is small v, and z direction is w. Here u, v, w are the velocity components in x, y, z directions respectively. Dx is the length of the element in the x direction, dy is the length of the element in y direction, dz is the length of the element in z direction, right? This is about the diagram, right? And rho is the mass density of the fluid element, rho is the mass density of the fluid element, right? This is about this elementary small strip, right? Now mass of fluid entering the phase A, B, C, right? What is the, in this case, what is the mass of fluid in the entering in the x direction? What is the mass of fluid leaving from the in the x direction? What is the mass of fluid entering in y direction? What is the mass of fluid leaving from the y direction? And what is the mass of fluid entering in z direction? What is the mass of fluid leaving from the z direction? These 3 points we are going to discuss here. Here in the first case, mass of fluid entering the phase A, B, C. This is the phase A, B, C, D. Mass of fluid entering the phase A, B, C. Mass equal to, already I told you, mass equal to mass density into velocity in the x direction into cross sectional area. Volume is also nothing but discharge. The discharge equal to velocity into area. Therefore mass of fluid entering in x direction is equal to, or mass of fluid entering in the phase A, B, C, D is equal to what is the formula? Mass density, that is denoted by rho, and velocity in x direction, that is equal to u into area of this surface, area of this face is equal to, this is dy a, this is equal to dz, dy into dz, this is the mass of fluid entering in x direction. Next one, mass of fluid leaving in the x direction. That here already we have determined mass of fluid entering in the x direction is equal to rho is the mass density, v, u is the velocity of flow, dy into dz, dy into dz is the area of the surface. Right, this is the mass of fluid entering in x direction. Mass of fluid leaving from the x direction means mass of fluid entering in x direction plus differentiation of mass of fluid entering in x direction with respect to dx, because that is entering in the x direction, into distance traveled, that is the dx. Okay, please, mass of fluid leaving in x direction is equal to, mass of fluid leaving in x direction is equal to mass of fluid entering in x direction, mass of fluid entering in x direction plus differentiation of mass of fluid entering in x direction divided by dx, that is in the direction dx, into dx means that is the distance traveled. This is the mass of fluid leaving in the x direction, right? Mass of fluid leaving in the x direction is equal to rho into mass density into u is the velocity of flow in x direction into dy into dz plus differentiation of mass of fluid entering with respect to dx into distance traveled dx. This is the mass of fluid and leaving in x direction. Then mass of fluid entering we know, and also mass of fluid leaving also we know the formulas. What is the gain of mass in the x direction? Gain of mass in the x direction equal to mass of fluid entering minus mass of fluid leaving. Right, what is the mass of fluid entering in the x direction? Rho u delta y into delta z minus, what is the leaving? Rho u dy dz plus d by dx of rho u dy dz into dx, right? Then minus, this is the minus into plus minus, therefore this is plus value, this is minus value. Finally we have minus dou by dou x of rho u dx dy dz. This is the gain of mass in x direction. Gain of mass in x direction equal to, this is the formula. Here also same, gain of mass in x direction is equal to inflow minus outflow. This is the inflow, this is the outflow. Then finally we have the gain of mass in x direction is equal to d by dx of rho u dx dy dz. Right? This is about mass of fluid entering in x direction, mass of fluid leaving in x direction, and gain of mass, the liquid traveling from in to out. This is we have derived. Next point, mass of fluid entering phase A, B, E, F. That means in the y direction. That is in the y direction. A, where is A, B, E, F? A, B, E, F. This is the y direction. Mass of fluid entering in y direction, mass of fluid leaving in y direction. This is also same formula, same style, but only direction is changes. So therefore mass of fluid entering in y direction is equal to mass density in the y direction, velocity is v, into what is the phase? Dx into this is dz. Dx is the into dz is the area. dx into dz. This is the mass of fluid entering in y direction. Similarly, mass of fluid leaving in y direction is equal to mass of fluid entering in y direction plus differentiation of mass of fluid entering in y direction with respect to dy into distance traveled is equal to dy. Right? Like that, mass of fluid leaving is equal to rho v dx dz plus d by dy of rho v dx dz into dy. Right? This is the mass of fluid leaving, equation number 2. This is the mass of fluid entering. Gain of mass in the y direction is equal to mass of fluid, that means inflow minus outflow, or mass of fluid entering minus mass of fluid leaving. Right? Similarly, same style, this is the mass of fluid inflow, mass of fluid leaving, this is the outflow. Next one, another case is the z direction. This is the z direction. Here also same formulas. This is the z direction. Right? In the z direction, mass of fluid entering in z direction is equal to same formula, rho into velocity in z direction is equal to w into dx into dy. This is the area. This is equal to dx. This is equal to dy. That is the area of the face BCGF. Therefore, this is the mass of fluid entering. Mass of fluid leaving is equal to, in a z direction, rho w dx dy plus d by dz. That means that is in the z direction, rho w into dx dy into distance traveled is equal to delta z. Therefore, gain of mass in z direction equal to inflow minus outflow. Inflow, this is the inflow, this is the outflow. Right? Inflow minus outflow, rho into w into dx dy minus this is minus rho w dx dy minus into plus minus, that is equal to d by dz of rho w dx dy into dz. This is minus value, this is plus value. Finally, we have minus of d by dz of rho w dx dy dz. This is the gain of mass in the z direction. Right? Net gain of mass. What is the net gain of mass? We have gain of mass, already we derived. Gain of mass in the x direction, gain of mass in the x direction, gain of mass in the y direction, and gain of mass in the z direction. What is the net gain of mass? Net gain of mass is equal to net gain of mass is equal to, this is the gain of mass in x direction plus gain of mass in y direction plus gain of mass in z direction. Right? Now here dx dy dz, here is also dx dy dz, here also we have dx dy dz, therefore dx dy dz taken out, therefore d by dx of rho u plus d by dy of rho v plus d by dz of rho w, this is dx dy dz. This is the net gain of mass if the fluid passing from or moving from one direction to one point to another point in x direction, y direction and z direction. Next one, this is one more point here. Mass is neither created nor destroyed in the fluid element. Mass is neither created nor destroyed in the fluid element. In this case, what is happening? The gain of mass in the fluid element must be equal to the rate of increase of mass, mass of fluid in that element. Right? Already we know net gain of mass. What is the rate of increase of mass? That we are going to determine. Then equating these two, finally we have the three-dimensional continuity equation. Right? This is a mass of fluid of the element. What is the formula? Mass equal to mass density into volume. This is the total element. Mass is equal to mass equal to mass density into volume. Volume is nothing but dx into dy into dz. This is the mass of element or mass of fluid element. Right? This is the mass of fluid element. Next, rate of increase of mass of fluid element is equal to differentiation of this mass. We have the rate of increase of mass of the fluid element. That differentiation of this one, that is d by d t, that is with respect to time. With respect to time, rate of increase of mass means this mass of fluid differences with respect to time. Then we have the, this is equal to rho dx dy dz. This is the rate of increase of mass. This is the rate of increase of mass is equal, this is the formula, or rate of increase of mass is equal to d by dt rho dx dy dz is the rate of increase of mass of fluid. Now we are going to equating these two, because the gain of mass must be equal to the rate of increase of mass. What is the gain of mass? Already we have derived. This is the gain of mass. This is the gain of mass, that is minus of this value. So already we have taken, these are taken out. This is the in x direction gain of mass, y direction gain of mass, z direction gain of mass with minus, right? And this is the rate of increase of mass. This is the formula here. Dx dy dz is equal to dx dy dz. Finally we have, these are the terms, right? Therefore finally we have d rho by dt. This is the d rho by dt plus d by dy of, sorry, this is x, this is x, d by dx of, this is also u, not v, right? D by dx of rho into u plus d by dy of rho into v plus d by dz of rho into w is equal to 0. This is the continuity equation in three-dimensional flow. D rho by dt plus d by dx of rho u plus d by dy of rho v plus d by dz of rho w is equal to 0. This is three-dimensional continuity equation. This is also known as Cartesian coordinates equation in Cartesian coordinates. This is about continuity equation in three-dimensional flow. Right now, this equation is applicable. This equation, continuity equation, already we have derived, right? That equation is applicable for steady flow, applicable for steady and unsteady flow, uniform and non-uniform flow, and compressible, incompressible flow. But here in case of steady flow, what is happening? Dou v by dou t is equal to 0, or dou p by dou t is equal to 0, or dou rho by dou t is equal to 0. That means the density of the fluid do not change with respect to time at a point. Therefore, dou rho by dou t is equal to 0. In this equation, in case of steady flow, this is equal to 0. Are you clear? Steady flow means the rate of change of density with respect to time at a point. That means this is a channel or a pipeline. At a point, the rate of change of density or rate of change of velocity do not change with respect to time. Therefore, dou rho by dou t is equal to 0. Therefore, dou rho by dou t is equal to 0. Then we have this is the equation for the continuity equation. In case of steady flow, the continuity equation is dou by dou x of rho u, dou by dou y of rho v, dou by dou z of rho w is equal to 0. This is the continuity equation. This is the continuity equation in case of steady flow. Next, in case of incompressible fluids, what is the rho 1 is equal to rho 2. Density at one section is equal to density at the another section. That is applicable, that is in case of incompressible fluids. Rho 1 is equal to rho 2. Therefore, Therefore, this equation can be written as this is rho 1 is equal to rho 2 is equal to rho 3. Therefore, the continuity equation steady and incompressible flow, continuity equation for steady and incompressible flow in 3D directions is equal to dou u by dou y plus dou v by dou y plus dou u by dou x, dou u by dou x plus dou v by dou y plus dou w by dou z. This is the three-dimensional continuity equation, steady and incompressible fluids. This is the three-dimensional equation. Whereas in case of two-dimensional flow, the z direction velocity w is equal to 0. Okay. In z direction, the velocity of flow, the component of velocity w is equal to 0. Therefore, this term is equal to 0. Therefore, continuity equation in case of two-dimensional flow is equal to dou u by dou x plus dou v by dou z is equal to 0. Right? This is the continuity equation.